classic sort of interpretation and exponents problem. It shows up a lot in the IBAISL exercises. They really like to put, and here's the main idea, they really like to put variables on exponents. Like, they know that confuses people. They know it's hard to solve, but I'm going to give you a couple tools, or at least probably end up showing you the tool that I use in order to solve these exercises. Got it? So we have that a cell phone starts charging at 7 a.m. and while being charged, the percentage of power P in the phone is modeled by the function P equals all of this, where T, notice, important, T is the number of hours after 7 a.m. See? So for part 4a, we need to find the percentage of power in the phone at 7 o'clock. So the approach of these exercises, or what they ask for, honestly, in my opinion, is pretty much always the same thing. See? Part A tends to be like, what's the initial amount? What's the initial power? What's like, here's the thing. See? Here's the main idea. The variable T is the number of hours after 7. And so if they're asking for the power at 7, notice, T is after 7. This is for T. T is after 7. And they're asking for the power at 7. Well, if you are at 7 and T has to be after 7, T has to equal 0. Makes sense, doesn't it? And so that's the first sort of thing you have to acknowledge and recognize. A lot of people here freak out because they say, ugh, I have A and I have T. It's over. I'm going over to the next one. See? However, it's friendlier than what you think. For part A, quite literally, you just plug in T equals 0. And the moment you plug in T equals 0, everything becomes much more friendly. And you might be thinking, this guy's crazy. How is it that for part 4a, I end up with P equals 100 minus 60 times A to the power of negative 0? How is that going to be friendlier? What the heck is happening? I don't understand. See? Guys, I know this looks nasty, but it's a lot friendlier than what you think, because first of all, negative 0 isn't really a thing. So let's make it a little bit more friendly on ourselves. So let's put it as just A to the power of 0. See? And the next thing we have to do, which you probably have memorized, is that anything to the power of 0 is simply going to be 1. So this ends up being as times 1. So I end up with 100 minus 60 times 1, so which is basically just 100 minus 60. You end up with P equals 40. So for part A, quite literally, you're going to see it's not that bad. 40%. See? So P equals 40 means that for part 4a, you end up with 40%. Now, I probably went a little bit fast here, and there's more than one of you saying, what the heck just happened there? See? So, anything to the power of 0 equals 1. If you want to memorize it like that, you can. If you want a quick explanation, I will give it to you right now. If you want to skip the explanation, or you already know, you can skip ahead a minute or two. Point is, in math, it's a lot of times called, more than a study of numbers, it's called the study of patterns. See, in math, there's a lot of different patterns that you can identify and learn and associate to. So when you're dealing with, for example, exponents, because we are talking about a 0 on the exponent, see, if you have, for example, 2 to the power of 3, this is 2 times 2 times 2. ¿Cierto? Now, 2 times 2 times 2, what's happening here is that you end up with 8. Now, the step before that is that you end up with 2. Actually, no, yeah. You end up with 8. ¿Vale? 2 squared, you end up with 2 times 2. That gives you 4. 2 to the power of 1 ends up as 2. That gives you 2. And 2 to the power of 0, you end up with only 1. See? Now, what is happening in the in-between step? ¿Cierto? Because here I'm showing you the in-between step, and over there I left it empty. So what's happening? Well, what's the pattern that arises here? The pattern that arises here is, notice, if I want to go up, from 2 to the power of 0 to 2 to the power of 1, you have to do times 2. If you're going to go from 2 to the power of 1 to 2 to the power of 2, you have to times 2 again. You have to times 2 again. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Makes sense. And if you want to go backwards, you have to divide by 2. So 8 divided by 2 gives 4. 4 divided by 2 gives, gives 2. 2 divided by 2 gives 1. And so, it's because eventually you divide the number by itself. Okay, but what's this in-between step that this guy online wanted to show me? The in-between step is that in math, it is a rule that all numbers have a times 1 next to them. Every single number has a times 1 next to it. And so what's happening here is that, for example, there when I divide by 2, you're getting rid of one of the 2's, you end up with 2 2's, ¿cierto? Here when you divide by 2, you're getting rid of one of them, you end up with only 1 2. And here when you divide by 2, now you end up with no 2's. You end up with only 1. Because this 1, it's a math rule, all numbers are always being multiplied by 1. I forget the fancy math name that it has. It was like the identity something. But point is, whenever you have an exponent as 0, it will equal 1 because you only end up with the 1. See? The other way you can sort of memorize it is that eventually you divide itself by itself, because in this step here, when you divide by 2 to go down, you end up having this 2 divided by 2, you end up with 1. You end up with itself divided by itself. And yes, this does happen everywhere. 3 squared is 9, 3 to the power of 1 is 3, and 3 to the power of 0 is 1, because if you divide by 3 each time, eventually, right here, you end up with 3 divided by 3. I end up with 1. See? Enough blah blah. Anything to the power of 0 equals 1 for part 4a. Easy peasy. 40%. Then they tell us that the percentage of power in the phone reaches 75% at 8 o'clock, and to find the value of a. And so this, although it looks very, very nasty, it's a little bit more friendly than what you think. See? So you have to have, for all these exercises of variable and exponent, it's really a very hard context problem. That's what I think. These variables and exponent problems is really just a very hard context problem. And so notice, when they tell you that the percentage of power in the phone reaches 75% at 8 o'clock, well, which are your variables? You have your t, which is hours after 7. And your other variable is p, which is power. So when they tell you that it reaches 75% at 8 o'clock, all they're really telling you is that when, it's actually a little bit backwards, when t is 1, because we're talking about 8 o'clock, so 8 o'clock is 1 hour after 7, so when t is 1, p is 75%. Will you look at that? Wow, that's crazy, isn't it? And technically, I can't just plug it in as 75, because all of this is in percents. I can leave it as p equals 75, see? But point is, the hardest part about these variable and exponent problems, for my interpretation, is that it's a very hard context problem. So the moment they give you that you have 75% at 8 o'clock, this is the information that they're sharing with you. When t equals 1, you end up with p equals 75. And if you plug that into your calculator, you end up with 75. Actually, we're probably going to need a little bit more space for this. See? So my formula is p equals 100 minus 60 times a to the power of negative t. And they just told you that when t equals 1, p equals 75. See? That is the main information that they gave you. So if I plug that information here, you end up with 75 equals 100 minus 60 times a to the power of negative 1. And from here, you need to solve. See? Now, you have a negative exponent. So that is another challenge we have to face. We just talked about exponents equaling 0. Now we have to talk about negative exponents. Negative exponents are not that harder, and we can follow the same pattern. And so the pattern, which was going downwards, ¿cierto? Which was also subtracting my exponent by 1 each time, ¿cierto? If we do it one more time, so if you divide by 2 here, you should end up with 2 to the power of negative 1. And so notice, if each of these times I was dividing by 2, dividing by 2, dividing by 2, well, what is 1 divided by 2? It's 1/2. Ah, okay. So 2 to the power of negative 2, it's going to be 1 divided by 2 times 2. 1 divided by 2 squared. 1 divided by 4. Not that hard either. Or is it? See? So, ladies and gentlemen, point is, when you have a negative exponent, the big thing you need to associate it to is that you are effectively flipping it. So, negative exponents, let me write it here actually. Negative exponents flip your number. See? Let me give you a couple examples because I think through examples it makes a little bit more sense. If you have, for example, x to the power of negative 2, you flip your number so you end up with 1 divided by x to the power of 2. If I had 3 times x to the power of negative 4, the 3 stays up top because the 3 is to the power of 1 and it's positive, so it stays the same. But down below you have x to the power of 4. So whenever you have a negative exponent, it flips your number. See? Even in the scenario where you have 1 divided by x to the power of negative 7, you're flipping your number. And so if it's on the bottom, now it ends up at the top. So guys, the negative exponent, all it really does is flip your number and the exponent like follows it. See? So down here, you have a to the power of negative 1. All that's really going to do is that you're going to end up with 60 up top and a on the bottom. Just like this. Nothing else, nothing more. A is on the bottom and the exponent followed it. It's to the power of 1. Now I'm not going to write a to the power of 1 because it's obvious or redundant, but that's where the exponent went. See? So that's the first step, understanding that the negative exponent is going to be flipping it. And the next big thing we have to do is that, this a on the bottom is like, it's like really annoying, isn't it? It sucks. No one likes it. No one likes fractions, let's be honest. But here we are, you gotta do what you gotta do. So, whenever you have an annoying variable on the denominator, and you're having trouble solving it from here, what you can do is multiply everything by a. Because in this step, if you multiply everything by a, golden rule of algebra, you have to multiply everything by a, ¿cierto? You can't multiply just one term by a, you gotta multiply everything by a. Although you end up with a bunch of different a's, this goes away with this, and you end up with 75a equals 100a minus 60, which might not look too pretty because you have a bunch of a's going around, but it's much better than having an a in the denominator. So that is the other big hint. The first thing we learned here is that negative exponents, they flip your number. So the a went to the bottom. And if you have a variable in your denominator, which is something that no one likes, one way to solve for that is just multiply by the denominator. Multiply everything by a, get rid of that fraction, get rid of that denominator. You end up with 75a equals 100a minus 60. And I like to keep things positive, so I'm going to do minus 75a to both sides. What you end up with is 0 equals 25a minus 60. You can do plus 60 to both sides. So you end up with 60 equals 25a. Divide both by 25. A equals 60 divided by 25, which is, I cannot do quick maths there, 2.4. See? So lo and behold, a is 2.4, not that hard. See? Yeah, that is for part B. We just found that a equals 2.4. The big challenge there was handling negative exponents, fractions, stuff like that. And now for part C, you need to draw the graph of p equals blah, blah, blah on the following set of axes. Now, the first sort of strategy whenever you need to draw the graph is that you plug in x values and you get a bunch of different y values and you graph from there with all different points that you get. See? But work smarter, not harder. Your TI-84 is literally a graphing calculator. There's a button on it that says graph. Isn't that amazing? The future's now. Anyways, if you want to draw this graph here, now you can graph it because you just found that A is 2.4. So really what you need to be graphing is 100 minus 60 times 2.4 to the power of negative t. And this is graphable because there is only one missing variable. And so if from here you go to your y equals, you can plug in 100 minus 60 times 2.4, which is the a, to the power of negative your variable. ¿Cierto? Negative t, negative x, whatever. So now it's graphable. And notice, a big part of the IB, whenever you graph, is that your graph has to be accurate. It has to be good. It has to be nice. That it? And one of the ways to make it look nice and etc. Usually they have a couple of points, and let me actually show you, ¿cierto? One of the points tends to be that you have the correct general shape, ¿cierto? If I were to draw something like this, it would be completely wrong. It's off, ¿cierto? So have the correct general shape. And the other thing that can help you a lot is that you write down the points that you're cutting through. And so what I tend to suggest whenever you have to sketch or graph is, first of all, get the general shape, ¿cierto? You should be nailing the general shape of it. That's pretty standard. But the other set of points that a lot of people forget is that you should be putting the key points onto your graph. See? So what I would have done here is quite literally put there, I would put the point 0,40 right onto my graph. I would put the point 1,75 because we found it earlier, ¿cierto? They gave it to us right here with what's in green, ¿cierto? And well, this last part is a little more advanced, but just putting a couple key points is going to give you full credit. See? So popping the general shape, putting the key points, makes sure that you get easy points on the graphing section. See? I will never forget one of the days that I was in math class. ¿Cierto? I also took the AB back in the day. And my teacher, the warm-up problem was to graph. ¿Cierto? And so we were all graphing, and everyone was done in like a minute. ¿Cierto? It was very quick. And then when we were done, he told all of us, like, you like all failed. See? And we were like, what? Like, we all had the same looking graph, but we all failed because we did not point out at any moment the key points. So keep that in mind. Getting the general shape is half the game. The other game is nailing the key points. So have that in mind for graphing, ¿cierto? Plotting them onto the point, like signaling it like this, is a very good idea for you to get full credit. ¿Vale? So, that being said, right here, it goes from 0 to 125. So what that is basically saying is that your y min is 0 and your y max is 125. And your x min is also 0 and your x max is 5. Why do I mention this? Because that right there helps you define your window. So before pressing graph, or actually better said, if you press graph, more likely than not, you might be able to see your graph, but you're not going to see it how you want it to, ¿cierto? This exercise is asking you to draw the graph onto these dimensions from 0 to 125, from 0 to 5. And over here, it doesn't look like it because my window is off. So go to your window. Your x min, as we just said, is 0. Your x max is 5. Your SCL, just always leave it as 1. Okay, please don't change it. Your y min is 0. And your y max is 125. See? Now, actually, the SCL is something that you sometimes have to change. Let me explain it. Here, you jump from 0 to 1, 1 to 2, 2 to 3. And so each of these sort of dotted lines is 1. See? So your x SCL is 1 because each of these dotted lines increases by 1. While your y SCL, well, by how much is it increasing? It's increasing by 25. 0 to 25, 25 to 50, 50 to 75. So actually from here, if you want to have it like ultra perfect, SCL for the y, oops, for the y is 25. See? So now we press graph, bada bim, bada boom. Now it looks a heck of a lot like the answer key now, doesn't it? See? And so from there you can go ahead and now you can plug in, or when I'm plugging, you can go ahead and draw. See? So on the one hand, I will get the general sort of shape very easily, going like this. Boom. But more importantly, for the full credit, remember, where are you starting? I'm starting at 040. How do you know that you're starting from 040? Because from part A, that's what I found out. You also know that you have the point 1 and 75. ¿Cierto? Not drawing a scale, but it doesn't matter as long as you put the points. You also know that you have the point 1,75 that comes from part B. See? And so that is probably good enough. And the last thing you have to notice is that there's like a line that it sort of like never reaches. ¿Cierto? It has a sort of, look at this, new concept, asymptote. So here you actually have a horizontal asymptote. I mentioned this because it's very common for exercises with variables on the exponent to have these sort of horizontal asymptotes and stuff like that. So all that's really happening is that right here, it's a number that your function will never reach. That's basically what an asymptote is. It gets extremely close to it, but it's never going to reach it. If I press trace and I go all the way to the right, notice as my x value increases, my y value gets very, very close to 100, but it'll never reach it. You can go on forever and you're never, ever actually going to reach it. See? Just to show you so that you trust me. Well, by now you should probably trust me. But point is, you're never going to reach 100 because you do have an asymptote at y equals 100. See? So, anyways, that was more for part C, but the introduction for horizontal asymptote helps for part D. For part D, you need to state a mathematical reason, ¿cierto? So I did talk about this a little bit. State a mathematical reason why the model predicts the percentage of power in the phone will never reach 100%. So there's two main things that are happening. One thing, or one way to answer, better said, is that you noticed in your graph that there's a number it never reaches, ¿cierto? Actually, even if you go to table, pressing second and graph, and you start scrolling down, you realize, damn, you really never reach, I mean, here it reaches 100, but it's really because it's 99.999999999, ¿cierto? Just so you trust me a little bit more on that, if you go to trace, it estimates it to 100 because you end up with 9.99999. See? So the fact that on the table showed 100 probably confused a couple of you, but point is, it's putting 100 because you're reaching 9.9999999, and your calculator would rather leave that as 100. See? And so here we are already at x equals 14, which is roughly where my calculator was putting it as 100 already. ¿Cierto? And so it's not that it's actually, oh, there we go. It's not that it's 100, it's 9.999 something. See? Anyways, one argument you can do here is that you notice they have a horizontal asymptote. See? That's this first sort of argument that you can give. It'll give you full credit. Bada bim, bada boom. And the other one that, for me, it's actually harder to spot. Maybe for others, it's easier. For me, I'm a visual guy, so the horizontal asymptote thing comes to me very quickly. But the other thing that can work out is that, A, you literally have 100 minus something. So the other mathematical reason is that you can say you have 100 minus something. And 100 minus something, well, of course, if you have 100 minus something, you're not going to reach that 100. And look at that. Over here, they tell you either you mention the horizontal asymptote at p equals 100, which is the same as y equals 100, ¿cierto? And you can describe it in words, ¿cierto? Or the equation literally has 100 minus a positive value, ¿cierto? And so it cannot equal 100. It's important, you guys, that for this part, although it's a context problem, they are asking for a mathematical reason. So if your reason is like, IB grader, have you ever met a phone that has more than 100%? That's not a good answer because they're asking for a mathematical reason, okay? You can't say battery may degrade or battery can't reach more than 100% because it's not a mathematical reason. Your mathematical reasons are either the asymptote or the 100 minus. Ladies and gentlemen, that is for number 4, and I hope it helped.